Hi, in this video, we want to take a look at logistic regression in Python. Okay, so here's a problem that we've got. We have a two-level categorical variable. So when I say that, this is going to be like success, failure, true, false, win, lose, heads, tail, two different levels. All right, so this is very different from the types of modeling that we've been doing before. Before, when we were doing regression, we had a whole range of numeric values. And there were, I could potentially have like one grader or less grader or a half grader, something like that. And I had a whole spectrum, a continuum of values for regression. Now, in this situation, there is exactly two levels. And what we want to do, we want to take in some data, and we want to predict which of the two levels are going to happen. So think about winning and losing. So if we're talking about, let's say, soccer, the case study for today is going to be using some soccer data. And we want to predict, win or lose based off of some data. And we want to, after we build the model, we want to make an inference about our modeling. What does that tell us about soccer? Okay, so what we're going to do, we're going to take an introduction to data science, a Python approach to concept, techniques, and applications. This is the name of the book. Here is the GitHub website, which includes the code that we're going over today in chapter 6. And we're doing logistic regression, and we're getting this from the scikit-learn package. All right, so there's several different ways to achieve this. For a regression model, the most common is logistic regression. Another one is probit regression. Probit regression is using like a Gaussian distribution aspect. My personal experience is that logistic regression is the best regression model for this type of problem. But if you're working with like economists, they have preferences on what's going on. There are alternative ways to approach it, but most of the time, for those who are working in application, we really don't worry that precisely about it. Logistic regression is one of the most flexible ways to approach this from a regression point of view. And so since it's flexible, it usually addresses our concerns as long as we have enough data. So we've got two levels, and we want to predict which of those two levels. So like win or lose on this one. And logistic regression has a formula where we've got a fraction where we've got E in the bottom of our fraction. If you remember what E is just a particular number. It has infinite long decimal representation. For us, we really don't care so much. Now, how this is actually built out, if you actually look at how the models are truly constructed, is that we are doing like a regression model on the log odds of winning. All right, so the odds of winning is going to be like the probability of winning divided by the probability of losing, and then we take the logarithm of that. That is the log odds. All right, so that you don't really need to know that too much, but just kind of keep it in the back of your mind that truly what we're doing is we're modeling the log odds of things. Now, why are we doing the log odds? Well, if I have a probability that's small and I divide by the probability of success is small and I divide by the probability of failure, then I'm going to get I can get potentially a very small number, and I need a logarithm to make it easier to handle. And it could also be if the probability is relatively large and I divide by the probability of failure is very, very small, then I get something big. Once again, the logarithm transforms it into an easier format to work with. And logarithms have a lot of nice properties to them, if you remember from college algebra, and that helps us interpret these models, but we're not going to worry about that today. Okay, so in our code, what we're going to be doing, and something that's nice about logistic regression is the model gives us a modeled likelihood of success for each individual point. So we get a modeled probability of success, a probability of winning out from the model, which is very good. So some statistical models, what they'll do is only feedback that we get is going to be like win or lose. It's all it tells us. It doesn't tell us like win by a lot, lose by a lot, win by a little, lose by a little. Like we won't know precisely what's going on. If we have a probability and we see that the probability is 0.999, we know that we can be very confident in the win. But if we see the probability is 0.5001, we're more likely to win than lose, but not by much. So if we see a probability of 0.4999, that's really close to a half. In that situation, we are more likely to lose than win, but it's not too far off from winning. If we see a probability of 0.00001, a very small probability of winning, then it's unlikely. Then we'd be pretty confident that it's not going to be a close game. All right, so let's go ahead and get Seaborn in so that we can do some visualizations. Let's get matplotlib for the same reason. Let's get NumPy and pandas for us. Now let's go ahead and let's build a special function. All right, so here I want you to see what does the curve look like for logistic regression. So I've got a fraction. I know we love fractions. Of 1 divided by, on the bottom, I have that E number thing down here. So this represents that number E from college algebra. And I have negative times an X. Okay, and this is a negative L, by the way. And so we're going to call that lambda, L for lambda. And then we have plus 1. Okay, so what's going on here is that this number here, no matter what value of X we put in, is always going to be a positive number. Okay, if I divide by something big, I get back something small. So if this term here, if this E part is big, the whole probability is going to be very, very small. If this E part is small, then the bottom is close to 1, just a little bit bigger than 1. If I divide 1 by something that's just a little bit bigger than 1, I'm going to have something that's just slightly less than 1. Okay, so conceptually, if I divide by something big, I get something small. Divide by something small, I get something big. All right, so if I divide 1 by something slightly bigger than 1, I get a number that's slightly less than 1. All right, and that's how we're going to get probabilities off of this. Off of this, the probability is always going to be less than 1, and it's always going to be greater than 0. So in this modeling system, we never say a probability is exactly 1. We never say a probability is 0. We always let a little bit of randomness in there, even if it's really, really, really tiny. All right, now what we want to do, I want to go ahead and I want to make some plots. So here I'm going to create some X values, and then I'm going to take the T, the Y, and the Z. Let's take a look at what happens. So here's X. These are the X values I want to graph over. What's T? Okay, and then what's Y? And what's Z? One thing that you'll notice is that all of these are potentially could be a probability. A probability is between 0 and 1. All right, all of these numbers for T, Y, and Z are between 0 and 1. And what we're doing, we're taking this logistic curve. I'm taking the X value, and I'm saying that the L is equal to 1/2 for T. And then I'm saying for Y, the L, the lambda, is equal to 1. And for Z, we're saying the lambda is equal to 3. All right, so now let's graph these and see what we get. Okay, so the green is when lambda is equal to 3. The orange is when lambda is equal to 1. And blue is when lambda is equal to 1/2. So what you'll notice is that it's steepest when lambda is bigger, and it's flatter when lambda is smaller. And what will happen if lambda was a negative value, it would actually, you see how it's like this? It's down low, then it comes up. Down low, then it comes up. It's down low, and then it comes up. If I have a negative value, it's going to be high, and then it's going to dip down like this. Okay, so in logistic regression, the lambda value tells us how steep this part of the curve is going to be. The y-intercept is going to, with the lambda value, is going to shift where that curve is left and right. Here, the intercept is equal to 0, and so this increased portion is centered at 0. It's the actual increased portion is the result of that lambda and the intercept together. All right. So let's go ahead and keep going. I want us to take a look at something. All right. What I want us to see on this one, on this plot, actually, you know what I'm going to do? Let's see if I can get all of this on one plot. No, it didn't do it for me. Let's do this. Let's see if I can get everything to work out. If I can't, I'll just explain it with that. Well, not going to work. That's all right. I wanted to do something on the fly. All right, let's say that I want to use linear regression instead of logistic regression. Okay, so let's think about it for a moment. Linear regression, that's a straight line. From college algebra, our straight lines go from negative infinity to positive infinity for the y-axis, correct? You know, I'm doing a college algebra mx, m times x plus b equals y model, mx plus b. It goes from negative infinity to positive infinity. So if I want to go through and I want to do modeling with this, I can see that I'm going to get my model is going to say that there's probabilities greater than 1. Does that make sense? Could I have a probability of 1.2? No, that doesn't make any sense at all. Down here, I see that my model says there's probabilities less than 0. Can I have a probability of negative 0.25? No, that doesn't make sense. So linear regression isn't going to do this for us. So what we need to do, we need a different shape of model. And that shape of model is exactly this S model that works so nicely for us. This handles a wide range of situations very well. All right, so let's go ahead and let's do a linear regression model. And we're going to put this on X and Y. And then we want to go ahead and plot and take a look at what happens. Okay, so check out what we've got. For this plot, you see I've got a bunch of X values going from negative 3 to 0, and then from 0 to 3. And we can see that all of these, the result of, so like if we say that 1 is a win, 0 is a loss, we can see all of these are wins, all of these are losses. And, you know, so something that is important in this concept is when the probability hits a half, it's like 50-50. We don't know which way it's going, if it's going up or going down. We don't know if it's going to be a win or a loss. But the moment it's greater than 0.5, we're going to classify that as a win. If it's less than 0.5, we classify it as a loss. All right, so now let's go ahead and take a look at a data set. All right, so this is going to be a soccer data from, I think it's a Spanish league, if I remember correctly. All right, so we want to predict winning and losing based off of the number of goals scored. So if I am like the offensive coordinator of a soccer team, and I want to figure out, okay, how many goals do we need to be able to guarantee a win? Well, we can use this data to achieve that. All right, so here's the original data, and we can get it from the textbook's website. I'm using the version from the textbook's website. I'm not using this one itself. And then we have several fields in the data set. So we have football, see, team or home goals, football team home goals, football team away goals, and then a football team result. Either it's a home win, a draw, or away win. And we want to visualize a scatter plot of home goals versus away goals. We want to take a look at what's going on and then do a logistic regression. So here I pull in my data. And so now I've got S is my data set that I'm going to be working with. I reduce the data from, so data underscore football is a full data. In S, all I've got is just the fields I'm interested in, the ones I'm actually going to use. So here we have the name of the home team, name of the away team, the goals for the home team, goals for the away team, and what was the final result. All right, so now let's go ahead and plot this. Let's see what happens. Okay, so here we have a scatter plot. Now, something that's really cool that we have here is that we put an alpha of 0.05. So what that does, you'll notice that the points are transparent. And this enables us to see which values are more common. So we can see that when it's darker, those are the more common results. So if I see home team with 1 goal, away team with 0, that's pretty dark. So that's a very common result. Now over here, when I look at home team 0 goals and away team 5 goals, that's very rare, but that is in the data set. So the home team got stomped on. And fortunately, you know, for the fans, that does not happen too often because it's a very light point on there. And if we look through here, like there's a point up here where 4 and 5, that's a high scoring game. That's pretty rare. All right, so now what we want to do, all right, so I want to convert this to, like home to wins losses. So I'm going to make a special function for this. So here is the max and the minimum. And what we're going to do, we're going to use the apply function to go through and go, hey, if the max is, you know, to figure out where, you know, who won, who lost on each of these. And so now we can see that we've got the win, how many points the winning team got and how many points the losing team got. And we can always see that the losing team has less or equal if it's a draw. All right, so now let's go ahead and start converting some things over. So let's take a look at X1. All right, so that is, we're taking the values from the wins columns. And here we're taking the values of the losses for X2. And then, sorry, that's right. And then here we've got Y1 and Y2. And we're using this, we're going to use this as our target variable for the logistic regression. So we're going to concatenate the X together. So we're putting X1, X2 together. And then we're concatenating the Y's. So now I've taken all the data. So before I had win-loss together, like in one collection. So I've got win-loss, so I've got home team, away team. What we're doing effectively, we're taking the data and we're building it like that. And so I'm taking, so if this is the, you know, win-loss score, I'm taking the data like this, and I'm taking it so that when for the winning, it's a bunch of ones and then it's a bunch of zeros, so that I have a much smaller data set to be working with. So now let's take a look at it. Oops. And so here we can see that number of goals, you know, the least is 0 goes up to 6. We can see that all the teams that scored 4 or more, or almost, okay, that one's almost not there, but it does show through. There is a point there, but all the teams that scored 5 or 6 points won, which, I mean, that's really not surprising. We can see that very frequently. This is a very dark point. It's very common for a team to, if they score 0 points, they're going to lose, which is not surprising because either they lose or they draw. A win really is not possible in that situation. And we can see it. We've got a dark point for losing when they score only 1 point. I mean, it's not surprising because if the opposing team scores 2, 3, 4, 5, or 6 points or more, potentially, then we know that they're going to lose. So let's go ahead and actually do logistic regression. So let's get the logistic regression function. Let's go ahead and fit it on X and Y. And then let's go ahead and do some plotting. Let's see what happens. All right, so here, what we've got going on is we went through and we fit on, so we built a model on our data. Now, what we want to do, we want to get an idea off of a range of potential values, which we call X tests in this data, what the probability of winning or losing is. All right, so here, this says that if a team scores 0 points, they have about a 10% chance of winning. And so here, of course, that would correspond to a draw. When they score 1 point, they've got a little bit less than 50% chance, so maybe about 0.4 likelihood of winning. When they score 2 points, now you'll see the probability of winning, that's a big jump. So something to notice is that at the middle of this, of that curve, middle of the S, that's where it's the steepest. So if I'm on the left of the middle of the S turn and I go to the right of the S turn, then all of a sudden I'm going to have a big jump in probability. You'll notice that if I go from this X value to this X value, that's not much of a vertical increase. And so for larger values in scoring, if we have a large value of goals and we score another goal, that really is not going to increase the probability of winning. But if I've got 0 goals and I increase that to 2, the probability of winning skyrockets. A bug is getting in my eye. Now, and you can see that when I model this, if we keep on scoring over and over and over and over, the probability of winning gets super close to 1, but it's not exactly 1. That allows for the situation where the other team is scoring like crazy. Let's say, you know, all of the defenders on both teams, including the goalie, get injured, or maybe all the goalies get kicked out of the game, and there's this crazy scoring. In that situation, it's just a crazy shootout, and somebody's going to win. But if both teams are crazy scoring, someone's going to lose. All right, that's all I've got for you. I hope this helps you see logistic regression. Remember, if I have two levels of a categorical variable to predict on, that is going to be a logistic regression problem very frequently. And so one of the big points to take away, regular regression really is unable to address this problem. We need that S-shaped bend to be able to tackle this. Take care. I hope you're doing well.